let's talk about the basic principles of air conditioning systems. So a vehicle's HVAC system is going to have to overcome multiple different things depending on its environment. So things that are considered heating loads on a vehicle, anything that's going to cool down the exterior and then eventually the interior of the vehicle, rain, wind, snow, ice, just cold ambient air temperatures. Those are all things that the heating system of our HVAC system is going to have to overcome. And as far as a cooling load, so these are loads that our refrigeration system will have to overcome. Radiation from the sun, so heat basically. High humidity is a big one that the air conditioning system tries to overcome because humidity makes us perceive that there's more heat around us because our body's cooling system isn't able to work as properly or as easily. That's our, us sweating and having the sweat evaporate off of our skin. And then there's the heat that the vehicle produces by itself just running. The engine's running, it at temperature it's somewhere between 190 and 210 degrees Fahrenheit. The exhaust system is hundreds and hundreds of degrees, also depending on where you're touching it. And then also in the interior of the vehicle, you have at least a driver in the vehicle, and as we add more passengers, just our temperature, we tend to be somewhere in the 96 to 98 degree range, which is hotter than what we would feel comfortable in, because most people like somewhere in the realm of 70 to 75 degrees is a comfortable temperature. So us just existing in a space that's enclosed will heat up the space. We're also breathing. Our respiration has moisture in it. We know that more than ever now. And so these are things that the cooling system will have to overcome as well. Ways the body gives up heat: convection, so that's our body's temperature. The temperature of our body often exceeds our ambient temperature, so heat just radiates off of us basically, which also ties into that radiation. So us just existing in a space creates a heat disbursement, and so we definitely are heating up our spaces in that way too. And then evaporation as well. So when we sweat, moisture builds up on our skin. When that moisture evaporates, it has to change from a liquid to a vapor. And that principle is the same one that our refrigeration systems work off of. We're trying to change states of matter, and to change from a liquid to a vapor, we need some sort of energy. And the most abundant source of energy is heat. And heat is a very, very pure source of energy. There's not much converting that needs to happen there. So that heat energy gets absorbed by the little water molecules of our sweat, and then those water molecules excite and start to move around more, and they eventually get excited enough that they break some of their molecular bonds and go off into vapor, no longer condensing with one another. So there's conduction. We also lose heat that way too. Anything we're touching, heat's going to travel from a source of heat to a colder area, because heat's the energy, just like electricity, the current flows. Heat is a similar idea there. The heat is this energy that flows. So just by touching something, heat from one source can be transferred to another. Convection, we're seeing the heat rising up above, and so that's just like the movement of air that's created because heat's trying to move around and find those colder objects, and also hotter objects tend to be a little bit lighter. So hotter air is not going to be as dense as cold air, and so it will rise above, basically floating on that cold air. And then radiation is heat that's just given off in any direction whatsoever, not specifically upwards. Conditions affecting the comfort of an individual would be the actual temperature itself, relative humidity, so the more humid it is outside, the more moisture in the air, the harder it is for our sweat to evaporate, so we don't cool as well. And then air motion. We all know that a fan feels nice when it's hot outside, and the reason for that is as we're sitting, perspiring, sweating, and also respirating, breathing, we're giving off moisture. And if there's no air circulation, well, we can saturate the air around us with moisture, and our systems won't work as well at cooling our body off. So if we're continuously bringing in fresh air, that would be perceived to have a lower humidity rate than what the air around us would have. That air motion actually helps accelerate the process of our own natural cooling mechanism. Temperature, I think, is an interesting concept to talk about for 1 second. When we measure temperature, we are actually measuring how much energy is present at a single spot. The higher the temperature, the more energy there is, and the little atoms and molecules that make up all the stuff around us, with that extra energy, they move around more. Everything's always kind of sitting there on some sort of a vibration, and the hotter and hotter stuff gets, the more excited it gets, and it moves more. And that's why water, which is a pretty dense, stable element there, that water, when we excite it enough, it turns into a vapor. And what we're doing is just taking tiny little bits of that water, exciting it enough so that it breaks away from the larger piece, and then it's light enough that it's able to be absorbed by the air, and it floats off and goes off some other place. So when we talk about temperature, we're talking about measurable energy. When we talk about a thing like hot or cold, we're talking about something that we can sense with our body. Something is hot to the touch, something is cold to the touch, something is not temperature to the touch, right? So think about a temperature being like a speedometer for atoms. So the higher the temperature, the faster the atoms are moving. Heat is the energy which causes an atom to be in motion. Temperature is a measurement of that atom's movements. And then sensible heat is any kind of heat energy that causes matter to change temperature. So it's something that we can measure, and we could feel it with our hand as something becomes warmer and warmer. We can sense that with our nervous system, but we can also measure that with our thermometer. Specific heat capacity is the heat needed to change the temperature of a substance. So how much energy does it take to change something by 1 degree Fahrenheit? The British thermal unit is a very common, what's the word I'm looking for, is a very common unit of measure for our refrigeration and heating systems. BTUs, oftentimes, like window AC units and other units like that, are actually rated by BTUs, so you can know how powerful the thing is. And then latent heat is another very important term that goes along with our sensible heat concept there. So sensible heat is heat that causes matter to change temperature, and we will be able to feel that change with our nervous system just by touching it. Latent heat, however, is the energy that causes matter to change states. So change from a solid like ice to a liquid like water, and then from that liquid to a vapor like steam. So when this happens, we're not actually changing the temperature. The freeze point of water is 32 degrees. So while an ice cube is melting, the frozen ice is staying at 32 degrees. It changes to liquid, and that liquid is still at 32 degrees. And then once it is liquid, that liquid can then start to change its sensible heat again, so the temperature of it can actually change. So the real idea here is that this latent heat is stuff that's going on in the background, and it's this energy that is being required to change from a solid to a liquid or a liquid to a vapor. Sensible heat is stuff that we can measure with our thermometer and is also noticeable to touch, right? We can't tell the difference between 1 degree Fahrenheit and 2 degree Fahrenheit, but we can tell the difference between 1 degree Fahrenheit and 20 degrees Fahrenheit. So there's our BTU. The definition for the BTU is the amount of energy it takes to increase 1 pound of water by 1 degree Fahrenheit. So 1 BTU would do that. And this is that reaffirmation of that concept that heat is what's traveling, because that's the energy. So heat's going to travel towards a colder area. Our states: solid, liquid, vapor. And then the points being made in this slide that ice is going to stay solid ice until it has risen its temperature above 32 degrees Fahrenheit. So during that raise of sensible heat, there's also going to be latent heat transfer that goes on as well. Liquid water that reaches its boiling point at 212 degrees. So a boiling pot with a thermometer in it is going to read 212 the entire time. If we could measure the heat of the steam coming off of that boiling pot of water, that steam would be hotter than the water because it has changed state, so it's now capable of reaching a higher temperature, and then off it goes. So in this line graph here, we're dealing with water in this case, just because that's something we're familiar with. And what's illustrated is on our y-axis, our temperature, and our x-axis is the amount of heat energy in BTUs that it's taken to reach these different points. So at point 1, we're starting with solid ice, so solid water, and it's at 0 degrees Fahrenheit. So that's definitely frozen. As we increase the temperature of that solid towards 32, there's no melting that's going on. It's still just a big solid block of ice. But we could measure a temperature difference as we go along with a thermometer. Once we hit 32 degrees Fahrenheit, now for that water to get any hotter, it needs to be able to move around. And to be able to move around, it's going to need to be able to change state of matter. As a solid, it's very, very tightly bound. There is still some movement, not very much at all. When we get to water, right, water is much more fluid, no pun intended there, than a solid is. And so those atoms and molecules will need to be able to move around even more. So, and that's what that temperature is requiring of them, basically. So to get to that point, we have to change states of matter. We're going to melt the ice. So if it took 16 BTUs of energy to get from 0 to 32 degrees Fahrenheit, but then it takes 144 BTUs of latent heat energy to change from 32 degree ice to 32 degree water. And this idea of it taking so much more heat energy to change states than to actually change temperature, this principle is going to be what gives our refrigeration system so much power and such a high capacity for changing the temperature of the air inside of our passenger compartment. As we take that water that's now 32 degrees and we heat it up to 212 degrees, which is our boiling point for water, it takes 180 BTUs of sensible heat energy to get there. So that's pretty substantial still, right? But we've also changed our temperature by a much wider spectrum than what we did with the ice. So it took more heat energy to change the water by more temperature, right? We can reconcile that. So at 212 degrees Fahrenheit, we're boiling, we're starting to change into steam, and to change all that water into steam, it takes 970 BTUs of latent heat. So that's super substantial. 970 to get from 212 degree water as a liquid to 212 degree vapor as a steam. So this is the area in which we'll be playing around in our refrigeration systems, just because we can flow liquid and vapor. It's really hard to flow a solid, and it also would take a lot more pressure in the system, making it more expensive. So they go with liquid and vapor, and a big part of the reason for that too, aside from the fact that like trying to flow solid frozen refrigerant through a system would be just absolutely laughable. This change of state between liquid and vapor has the highest draw for latent heat energy. It takes the most energy to go from liquid to vapor, or the most energy is given up when we go back from vapor and condense down into a liquid. So we're getting the biggest bang for our buck, is the short way of saying that. So if we take, let's say, a pound of water and we boil it, and it all turns into steam, we haven't changed the weight. We haven't gotten rid of any water. We haven't destroyed anything. We've still got a pound of water, but now it's a pound of water that's floating around in whatever room, or if we're outside. So if we were able to somehow catch all that steam, recondense it into water, and reweigh it, we would still have a pound of water. So, and that's just that idea. We're not destroying anything when we're changing states, and that's why our refrigeration systems, if we don't have a leak in it anywhere, shouldn't need to ever be recharged. That same refrigerant that got put in at the factory, if we had a perfectly sealed system and never leaked anything out of it, we would be able to run it for the entire lifetime of the vehicle, and we would never use up any of that refrigeration. Latent heat of condensation. This is just showing it in the opposite direction, and the only reason I bring this up is just to make it clear that if it took 970 BTUs to go from a liquid to a vapor, well, when we go from a vapor down to a liquid, we're going to need to give off that 970 BTUs of heat energy to reverse the process. So it's a one in, one out type situation. And the same idea there. Pound of vapor is a pound of water, yada yada. And our little thermometers are just measuring the speed of our atoms there. In our refrigeration system, since we're dealing with refrigerants, they tend to boil at something like R134a, I think it boils at negative 24 degrees Fahrenheit, if I remember correctly. So in our system, we would have to somehow figure out how to keep our system down at negative 24 degrees to be able to play that game between liquid and vapor. That's not going to be very easy. The easy thing to do is to completely seal off the system. It's just a big loop. And then we put in the compressor, one, to help flow the refrigerant, but it also raises the pressure of the system from our atmospheric pressure, which is like 14.7 psi at sea level, somewhere around 15, sometimes you'll hear people say. So we take that pressure of just like all the air and gravity and stuff like that pulling it down on us. We take that pressure, and with the AC compressor inside the system that's just filled with refrigerant and nothing else, we can raise the pressure in that system up to 150 to 250 would be fairly average on the high side of the system. So, we're talking 10, 11, 12 times as much pressure as what ambient pressure would be. So at ambient pressure, a refrigerant would evaporate around negative 24 degrees, and at our heightened pressure, which is 10 times plus what it would normally be, our refrigerant boils at a much, much higher temperature. We're talking somewhere around 150 degrees Fahrenheit. Could even be as high as 200 or 300 degrees, depending on the conditions that we find ourselves in. So that's a huge change. We've gone from negative 24 of a boiling point to, let's call it 200 degrees at a boiling point. So we're using the pressure to increase the boiling point, just like a pressure cooker does, and just like our cooling system on our cars do as well. We put a pressurized radiator cap on our system because if the car is hitting its operating temperature at 190, 210, well, the boiling point of just water, which could be used as a coolant inside a vehicle. The boiling point of water is 212. That's way too close to the normal operating temperature of our vehicle, and there will definitely be hot spots next to our cylinder and our combustion chamber that are hotter than 212 degrees. So we don't want anything flash boiling inside of our system, because that would make it so it doesn't actually cool anymore. So they raise the pressure of our cooling system so that the boiling point raises, and we're doing the same thing with our refrigeration system. So temperature also will change with pressure. Think about a diesel engine does not have any kind of ignition system. There is a piston moves down and draws air into the cylinder. The piston rises up with the valves closed, raising the pressure. And with that pressure, my atoms and molecules are now shoved closer and closer. And think about it, they're all wiggling because there's heat energy. And as they get closer, there's a friction that builds up as these atoms start to touch one another. And the pressure keeps going up, and the friction increases, so the temperature increases, which makes the atoms more excited. And the pressure is increasing because the piston's still moving up, and the temperature is increasing to the point where the air is so hot, all we have to do is inject fuel, and that hot air is enough to set the fuel on fire, causing a combustion event. Inside of our AC system, the compressor has pistons inside of it. We're going to pull in a vapor state refrigerant. We're going to raise the pressure of it with the piston by squishing it, creating more pressure. And when the vapor leaves the compressor, it's about 100 psi higher in pressure than it was before, and also about 100 degrees Fahrenheit hotter than it was before because of this friction that happens as we compress a material. We can only pull in vapor refrigerant and put out vapor refrigerant because we can compress a vapor. Think about back to our braking systems, Pascal's law. I cannot compress a liquid, so if I pulled liquid refrigerant into my system, in my compressor, that would be bad because the piston's going to move up and eventually it's going to run out of room and the liquid's going to be there and it's not going to move, and the metal of the compressor is going to move before the liquid of the refrigerant. So you want to make sure it's always vapor coming in and going back out. Alright, and let's take a look at that refrigeration circuit now that we're experts at refrigeration. So here is a very, very simple diagram, block diagram of our refrigeration circuit. The starting and finish line is our compressor. I'm going to take a vaporized refrigerant, pull it into my compressor, raise the pressure up to somewhere around 150 to 200 psi. That hot vaporized refrigerant is going to leave the compressor and it's going to go into our condenser. The condenser is up at the front of the vehicle right next to the radiator. So as we're driving along, or as the fan for the cooling system is turned on, air is going to pass through the fins of this condenser and it's going to cool off the refrigerant. So at that point we have a high pressure vapor coming in. That's super hot. Like if you touch this line, it would probably burn your hand. It comes into our condenser, and what comes out is a high pressure, hot liquid. So this was like outrageously hot, and this is hot. We maybe dropped 20 to 40 degrees across the condenser. And that was just enough to get our vapor refrigerant to turn into a liquid, right? So we gave off a whole bunch of latent heat to that outside air as we changed states of matter from a vapor down to a liquid. All right, so that's why we had to go through a heat exchanger, because we needed some place to get rid of all that heat energy. Then, once we leave the condenser as a hot, high-pressure liquid, we come into our expansion device. So we'll talk about these in much greater detail when we go through components, but the expansion device is just a little pinhole. Think about if you've ever used a spray can before. like you're using brake clean, or I don't know if people use hairspray anymore or whatever, but you're using this spray can, and it actually cools off because the liquid inside the can is turning into a vapor, right? We're atomizing it, turning into a vapor spray. And so ambient heat energy is being absorbed by this process that's happening, and we can feel the can get cold. So this is just like that little tiny pinhole spray nozzle right there that is going to cause a big change of pressure. So from my compressor to my expansion device, if I drew a line, this would be my high side, high pressure, because I have the compressor forcing out, and I have this tiny, tiny little hole that's limiting how much pressure can get through. Kind of sounds like an electrical circuit. I got a battery, and I have a resistor. My pressure, which is like a voltage, gets backed up between my little restriction and the pump that's producing any kind of flow or any impetus really for my voltage, or in this case my refrigerant, to start getting going. So high pressure side. Once I come through my expansion device, I've dropped my pressure greatly. So now I'm a low pressure, and with that low pressure comes a low temperature. So I'm now a low pressure, cold liquid refrigerant. This device here, there's nothing around here really providing enough heat energy for us to change states of matter as we go through there. We changed pressure, but there's not any. Where's all the heat energy? I don't know. It's nowhere. Not enough for all this refrigerant. So we have not changed states of matter. Low pressure, cold, liquid refrigerant comes through, and then into my next heat exchanger, which is my evaporator. The evaporator is the heat exchanger under the dashboard that the blower motor blows air through. So as the air passes through the evaporator, that cold refrigerant that's really low pressure starts to absorb this heat, and it gets to its boiling point, and it boils inside the evaporator, changing to a gas. So that's how it absorbs all that heat energy out of the passenger compartment, is it's changing states of matter inside the passenger compartment in this little heat exchanger. So it's just like a black hole for heat energy, soaking it right up, so it can change from a cold liquid refrigerant when it goes in to a cool vapor refrigerant when it comes out. And it better be a vapor refrigerant, because if it wasn't, when it gets into that compressor, it's going to go to town and start breaking it, because we can't compress a liquid. So I had a student, I think the first year I ever taught anything about refrigeration, looking at a chart similar to this, and he said if you draw a line between the compressor and whatever your restriction is, then you can see what's your high side, right, between the compressor and the restriction, and then the low side between the restriction and the compressor, because the low side, the compressor's pistons are moving down, trying to draw in that vapor refrigerant. So low pressure over here, just like the ground side of an electrical circuit. He also noticed if you draw a line through the evaporator and the condenser, you can see what side has vapor. Vapor comes out of the evaporator, vapor goes into the condenser. You can also see what side has liquid. Liquid leaves the condenser and enters the evaporator. So by just drawing that cross, basically, you can tell what what state of matter the refrigerant should be and what pressure it should be anywhere in the system. And then the last real takeaway from that is if it's on the high pressure side of the system, it's hot. If it's on the low pressure side of the system, it's cold. And I don't get into the intricacies of, oh, it's scalding hot, now it's just hot, super duper cold, now it's just cool. No, if you know hot, cold, that's going to be enough to get you through any kind of diagnosis you need to. All right, especially if we're just going off sensible touch. Now our systems, when we actually look at them in a vehicle, have a few more components to them. So in this case, here's an expansion valve system. Still have my compressor, but my restriction, or what they were calling their expansion device. But on this type of situation, my restriction is variable. So this has a valve in it that can make the size of the hole bigger or smaller. And we're still talking a pinhole here, but for our use, bigger, smaller. And so it can sit there and vary. And the way that it can tell what it needs to do is this little sensing bulb that is touching the outlet of the evaporator. So it's able to tell what the temperature is of the refrigerant leaving the evaporator. And so that way it can tell, well, if this is too warm, I need to add more refrigerant to the evaporator, cool things down a little bit more. If this is too cold, well, we run the risk of sending liquid refrigerant into our compressor at that point. So it's going to close its valve a little bit and make sure that we're metering the correct amount of refrigerant through that evaporator. Because if it's really cold outside and I just have the defrost on and the AC compressor is kicked on to help remove moisture from the air, because that evaporator, since it's cold, is going to have water bead up on it, just like a cold can of soda is going to have water bead up on it as well, because as the air cools down, the space between atoms and molecules for a liquid to build up diminishes, and so all of a sudden the liquid starts to condense and cause big droplets, and then it will eventually start to build up on a surface. So that happens in our evaporator here. In this system with an expansion valve, we have a receiver dryer, and that's between the outlet of the condenser and the inlet to our expansion valve. This receiver dryer would normally sit upright, not on its side like that. And you see how the straw for my input to the expansion valve is in the bottom? That whole point of that receiver dryer is to make sure that liquid refrigerant gets to the valve. Gas is going to pass through that restriction pretty easily, and so there's not going to be a big pressure drop. The liquid has a harder time going through, and that makes sure that there is a big change of pressure between my high pressure side and my low pressure side. And those are really the only notable talking points of what we would call a TXV system. A thermostatic, right? It's measuring the temperature of our outlet. Expansion valve. So it's a valve that expands based off of a temperature that it senses. So high pressure, hot vapor refrigerant condenses into a high pressure, hot liquid refrigerant, which goes through my expansion valve and becomes a cold, low pressure liquid. It evaporates in my evaporator as it absorbs heat energy from the passenger compartment, and then comes out as a cold, low pressure gas ready to go back into the compressor once more. This style system, which is becoming less common on vehicles, but had definitely played its part for many decades, is called the fixed orifice tube. So in this system there is a little tube put inside the tubing of the refrigeration circuit, and that has a little pinhole in it as well. And they call it a fixed orifice tube because the orifice, the tiny little hole inside of it, is fixed. This one does not change. And you can see there's nothing that's going to give it any kind of sense at what the temperature is on the outside of the evaporator. Not outside, but outlet of the evaporator. And because of that, the system is not as variable, definitely not going to be as efficient of a system. And also we run the risk of liquid getting into my compressor because, like I said earlier, we don't just use the AC system when it's hot outside. We also will use it oftentimes in the middle of the winter when we're trying to defrost our windshield and it's freezing cold outside. There's not really any heat energy in the vehicle. Hopefully that heater core that's in there very close by to the evaporator starts putting out some heat for us, which will be helpful. But this accumulator here, you can see, again, this, I don't know why they draw them like this, but it would normally be sitting upright in the vehicle. You can see that the straw here, that is the outlet going into the compressor, is poking up because it's trying to make sure it's only catching vapor and no liquid. the liquid can accumulate down here at the bottom for a little bit, and this is in the engine compartment. So the heat of the engine and the exhaust and all that kind of stuff will help boil off any kind of liquid refrigerant that's inside that unit, because we'll get up to operating temperature sooner or later. There are government mandates on that stuff. So right now I think we're somewhere around like the 5 to 7 minutes range from start when a vehicle should be up to temp. So you can see how that goes. Now, I've talked about how the system components have helped protect the compressor to make sure that we don't get liquid into it, but there's another way that the system can protect itself as well, and that is just by turning off the compressor. The compressor is belt driven, and there's a little electromagnet that turns on and pulls a clutch in, grabs the pulley, starts spinning the inside bits of the compressor to move the pistons and create flow and pressure. Well, if we get to the point where the system is cooled as well as it possibly can, to the point where we're worried about getting liquid into the compressor, or if we're worried about lowering the temperature of our evaporator so far that we start to ice up the outside of it, because we're trying to stay right around 32 degrees in that evaporator so it works as well as it can, but that's also the point at which water freezes, so we got to stay just north of that freeze point. Well, the easiest way to control this system is just turn it off. Oh, it's too cold, or we're going to get liquid into our compressor. Shut it off. That way we have time for the refrigerant to absorb more heat energy, and also we're starting to slow down the cycle. Even with the system turned off, because I've built up all this pressure here, it takes a while for it to equalize and stop flowing, but turning the compressor off is going to have a huge effect on the pressures and also the amount of flow that occurs. Safety precautions when working with refrigerant. Refrigerant evaporates at low temperatures, right? At ambient pressure, which would be whatever we're standing in the shop, it's going to evaporate at negative 24-ish degrees, and that's going to be more than enough to, if you open up a line by accident or open a bottle up and don't have it connected to anything, it's just going to immediately vaporize and fill the area that you're in. As it's changing states, it's trying to absorb heat energy from anywhere it can, and you're plenty warm enough, so if it touches your skin or eyes, it could freeze them, which has varying levels of discomfort. I've definitely gotten freezy fingertips before, which we live in Maine, so we've all felt what that's like. Luckily, I've not gotten freezy eyes before. That's going to require a trip to the hospital or a doctor. Also, something that is really important to realize is the refrigerant in a system is, once we release it, because it's going to expand so much because it's turned into a vapor, it can displace the air inside of a small space. If you're working on a car and you disconnect a hose and you're just in a one bay garage that's completely closed in, you'd want to open the door and leave the area, because you could actually pass out because so much of your oxygen has been displaced. If you're in a big shop, it's just going to smell real bad and everybody's going to dislike you, and you've also not done great things for the atmosphere, environment. But you're not likely to pass out because of it. In a classroom with a bottle, if the bottle got opened up, and that would totally fill up the classroom, and everybody would pass out if they weren't able to get out quickly enough. And it's heavier than air, so once it's settled down from being all excited, if the room that it's in has not been properly ventilated, it's going to settle down near the floor, and anybody who's down low like that, like someone working on a creeper, could be overcome by those fumes as well. So just some normal safety things we got to watch out for. If you do get refrigerant in your eyes or skin, most importantly your eyes, do not rub it. You created ice crystals, which can be sharp, so if you rub the area to try to warm it back up, or because it feels bad and you're trying, it's just a natural reaction, you could actually start breaking blood vessels and stuff because of those ice crystals that have been formed. Splash large quantities of cool water into the eye to increase the temperature. Our eye wash stations are set for around 70 degrees Fahrenheit, which would be considered cool water to us. And so we don't want to use super cold water because that's not going to make you feel any better. It'll be uncomfortable in a normal occasion. We also don't want to use hot water because think about washing your hands in hot water after they've been outside and really cold for a long time. That's very painful too. So the large quantities of cool water are going to help return whatever the tissue is to the right temperature and also help flush away any kind of chemicals or irritants that might be there. We're going to tape a sterile eye patch in place to prevent dirt from entering the eye because any injury to the eye is incredibly prone to infection, and that's the thing that actually tends to cause people to lose their eyes and things like that, or having some sort of trauma to the eye and then having it get infected after the fact. And then you will go immediately to a doctor or a hospital for professional care because you only have two eyeballs and we want to make sure we take as good a care of them as absolutely possible. Alright, so thanks for sticking with me, and I will see you next time.